Hello everyone, welcome to another video of the course. In this video, we are going to solve the problem number 4 and so on, depends on how much time we have today. So here is the problem number 4. Two coils are wound on a toroidal core as shown in figure P1.4. This figure, we have a circular shape iron core. The core is made of silicon sheet steel and has a square cross section. So the cross section of this iron core is a square. This is important. If the cross section is not a square, we cannot use two-dimensional finite element method properly. Okay, so we need to use three-dimensional FEM. But in this case, like the previous problem, we can use two-dimensional finite element method and solve this problem. So the coil currents are I1 is 0.28 ampere and I2 is 0.56 ampere. A. Determine the flux density at the mean radius of the core. The flux density. B. At the mean radius, assuming constant flux density, same as the mean radius over the cross section of the core, determine the flux in the core. Okay, again we have an important assumption. C, determine the relative permeability mu r of the core. So here you can see the dimensions. The inner radius of the core is 19 centimeters. The outer radius is 21 centimeters. So we can calculate the width, right, of this iron core. And also because its cross section is a square, we know the depth of the problem. The number of turns for the coil 1 is 600 and for the coil 2 is 300. So how we can calculate B flux density at the mean radius? Using the Ampere law, we can calculate H and then we can calculate the B. So how we can calculate H? So let me copy this. We can consider this integration path in the center of this iron core. So we have R1, R2. The average radius is R1 plus R2 divided by 2. So the length of this path in the center is equal to 2 times pi times R average. So if we calculate integral of h dot dl, right, considering this path, it is equal to n1 times I1 plus n2 times I2. Direction of the current is important. You know that this coil generates a flux in this direction and this coil generates a flux in this direction. So the direction of the flux generated by the coil 1 is in the same direction of the flux generated by this coil. So I considered this plus sign. Otherwise, we should consider negative one. So this is the current enclosed by this path. So you can write here, right? If you consider H equal along this path, the tangential component, H times 2 times pi r average is equal to this summation. And finally, we can calculate the value of the H. So when we know the value of the H, we can calculate B using this curve, the silicon sheet steel. As mentioned here, the core is made of silicon sheet steel. So we have HB curve. And for any value of H, we can use interpolation and find the value of the B. So after calculating H from this equation, we can interpolate the value of the B considering this curve given in figure 1.7. And finally, we can calculate the permeability, the relative permeability of the iron. This is the permeability and the relative one. We need to divide it by mu 0. How much is the core cross section? Is R2 minus R1 to the power 2. Yes, because the cross section is a square, and when we have this area and we assume a constant flux density, the same as the mean radius constant, we can calculate phi. So this is the phi, that is B times A. We consider it B constant. So we calculate integral of B dot dA using this equation. Also here you can see the equivalent circuit of this model that we have here. The direction of these magnetomotive force sources is also important, right? We have summation. So let's calculate quantities in MATLAB first, and then we use the ANSYS Maxwell software. So here, let me copy the code here and paste it for the problem number 4. We can edit the parameters. So the value of the I1 is given. The value of the I1, this is the current of the coil 1, 0.28. So 0.28. This is current of coil 1. So let's modify this also, this comment. And this is the current of the coil 2. The second one, I2, is equal to 0.56. 0.56. We have N1 and N2. So this is N1 and N2. The number of coil 1 turns, this is coil 2, 600 and 300. So 600 and 300. We have R1 and R2, 19 and 21. So we have these two parameters. R1, R2. This is the inner radius of the core. Inner radius of the core. The unit is centimeter. And this is the outer radius of the core. The outer. So we have this information from the problem. And now let's calculate H, the field intensity. So the outputs are H, that is equal to, let's write here H in center, is equal to N1 times I1 plus N2 times I2 divided by L center. So this is the field, magnetic field intensity, magnetic field intensity in center. The unit is ampere per meter. So what is the value of L center is equal to 2 times pi times R average. And this is the average radius. R average is R1 plus R2 divided by 2. So this is the average radius. Again, the unit is centimeter. And this is our average. So I want to calculate L center in meters. So I multiply it by 1e minus 2. This is the length of the flux line in the center. The unit is meter. So we have our average, we have L center, and we can calculate H. So when we calculate H, we should use interpolation to calculate the value of the B. But we need to have XY data of this graph to calculate if we are going to calculate it in MATLAB. We can use one-dimensional interpolation. So we will discuss. So here, let me highlight this part, comment it, and we don't need these 3 lines. Also, I need to calculate phi. So let's run the code. If I run the code, as you can see, what is the value of the H? 267. This is the value of the H center. So 267, if you look at this graph, for this H, for this value of the H, what is the value of the B? So this is for 300, right? And this is lower than 300. We can guess, right? It is close to 1.1 Tesla. If we are going to actually interpolate it from here. So let me copy this and draw a line. This is 300 and right, 267 is here. So this is around 1.1 Tesla, the value of the B after interpolation. So if I write here B center, this is after interpolation, B center equal to 1.1 Tesla. This is the flux density. Determine the flux density at the mean radius of the core. So this is the flux density at the mean radius. The unit is Tesla. So when we know B, we can calculate the permeability of the iron, that is B center divided by H center, right? We know that B is equal to mu H. So yes, you can calculate the permeability. And finally, what is the value of the relative permeability of the iron? Relative permeability, mu R, is equal to mu divided by mu 0. So the relative permeability, right, uh, should be determined for the part C. So if I run, as you can see, the relative permeability is around 3200 mu R for this iron core. 3200, right? Around this number. Anyway, so now let's calculate the flux assuming this condition, the constant flux density. So the area of the core is this one. The AC is R2 minus R1 to the power 2 times 1e minus 4, because I want to calculate it in meter square. So this is the cross section area of the core. This is meter square. And finally, what is the value of the phi? The value of the flux density in core is equal to B center times AC. So the value of the flux, the phi, is here. If I multiply it by 1e minus 1e3 is 0.44 milliweber. So let's multiply this by 1e3 and calculate it in milliweber. 0.44 milliweber. So we solved this problem analytically considering these assumptions and this HP curve. Now let's solve this problem in ANSYS Maxwell and compare the results. So generate a new project and add a 2D design, a Maxwell design. So we need to draw this geometry first. Draw a circle like before. What is the radius? Is R1. The value is 19 centimeters. Now let's draw another circle. This is R2 is equal to 21 centimeters. So we can select circle 2 from 1 and subtract. Okay, so you can see these values, R1 and R2. Okay, R1 and R2. So let's save the project in the same folder here for the chapter 1. This is problem number 4. And now I should create coil arms like before. Two for the coil 1 and two for the coil 2. So here I can use this method. Let's select draw a line. So I draw a line here to here. Then I can extend this polyline. So right click, select set edge type, center point arc, and again straight. You should right click. So double click here to close this. Now we have this face. So here I set this point, the x coordinate of this point equal to R2 plus, let's consider a width for the coil, width of the coil plus 1 centimeter. Or we can use a lower number, 0.5 centimeter. No difference. Let's consider 1 centimeter. Width of the coil, consider 2 centimeters. And this arc, let's set its angle equal to 30. So now I can select this face, duplicate mirror. So click on origin and move the cursor in the direction of the y-axis. So we have these two objects. We can select these two, unite. Then draw another circle. The radius of this circle 3, let's set it equal to R2 plus 1 centimeter. Select this one, circle 3, and subtract. Yes, so this is one side of the coil, and I can calculate another one using the same procedure. Okay, or I can consider a more smart method. So let's do the Control Z. Here, instead of this subtraction, I can draw another circle, set the radius equal to R1 minus 1 centimeter. So select this circle, subtract, then this object, we can subtract. Finally, we can subtract it from another circle. So let's draw another circle. Set the radius equal to R1 minus 1 centimeter minus width of the coil. Select this object, subtract this one, subtract, and select this object, edit, Boolean, separate bodies, right? So we can generate this geometry and we can select these two objects, consider the same geometries for the coil 1 also, right? So let's set the materials and use proper colors for these objects, the copper, and we need to define excitations. So here, as you can see, you can check the direction of the excitation. For this side, the direction of the current is into the paper for this one. So how much is the total current passing through this region is N1 times I1. The reference direction is negative. So N1 is 600. the unit is none. I1 is equal 0.28 ampere. 0.28 ampere. So we have the same value for the next coil arm for this one. So assign excitation, but the direction is positive. For this one, again, as you can see, the direction of the current is into the paper. Assign current. This is N2. I2 negative. N2 is 300. The unit is none. I2 is equal 0.56. 0.56 ampere. So let me copy this. For this one, what is the amount of total current? Is N2 I2. The direction is positive. So you can check into the paper, out of the paper, into the paper, out of the paper. So now we can draw the region, but also we should set the materials for this object. I select copper. And what about this one? Here we have this material, silicon sheet steel. Do we have this HP curve in ANSYS Maxwell library or not? So let's check. Right click, assign material. We have a bunch of material in library of the ANSYS Maxwell. So here you can see the material library. We have different materials, right? Also for iron, silicon core iron, yes. So from different manufacturers, the cast iron, okay. So I am going to consider one material random. So let's consider a steel 10 10. So before selecting this material, let's check its properties. The relative permeability is nonlinear, is not a constant. So let's check the HP curve. Here you can see the HP curve of this material. And what is the value of the B for this material when the value of H is around 267. So I need to move here, here, and lower 1.3 Tesla. You can follow this number. So 1.1, if we need to get 1.1 Tesla, the value of H should be this one. The unit is ampere per meter. So this is not close to this material that we have here. I'm going to select kilos material. So let's search silicon iron core. We have different materials, different grades for the cast iron, A, B, C. So what is this one? HP curve. Let's add 1.1 Tesla. Yes, this is close to what we need. 1.1 Tesla, the value of H is 310. So let's continue with this material. Okay. Yes. So this is the core material that we selected, and we have a nonlinear HP curve for it. This is the silicon core iron, and this is the HP curve. Even we can export the HP curve and read it in MATLAB and plot the graph. So let's do it. Export data set. So this is BH data in the tab version. So yes, this is the exported value, and let's copy the data here. Let's define also this variable bh data equal to this matrix. So the first column is the h data. So h data is, we need to get the first column of this matrix. So all rows and the first column transpose, and this is for getting the second column b data. So let me run this m file and plot h data b data. Yes, this is the graph. We don't have the exact graph here, but I am going to write the coding and select default HP curve. So when we have one HP curve in MATLAB like this, how we can do one-dimensional interpolation? We can use this function interp1. This is one-dimensional interpolation. H data, B data, and the value of the H that we are going to do interpolation for it. For example, if I write here 300, the value of the B is equal to 1.01. So here, if I copy this and paste it here, this is H center. So we can do the calculations considering the HP curve that we imported, not exactly this one. And here, plot operating point. Here we can plot this graph, set the x label. What is the x label? X label is H, the unit is ampere per meter. And the y label is B, the unit is Tesla. This is y label. So let's write this, hold on, box on, just to plot graphs on each other. And then I want to plot this operating point. H center, B center, show it with this marker B. So if I run the code, as you can see, this is the HP curve and this is our operating point. Yes, this is the operating point. So let's run the simulation in ANSYS Maxwell. Before that, like before, I need to draw a region. Let's consider 100% and apply boundary conditions to this edge. Everything is fine. We can add the solution setup and analyze. So when we solve this problem, the problem is solved. We can select the iron, plot, B vectors. Okay, you can see the B vectors. The direction of the B is clockwise, right? Due to the direction of the excitations that we discussed inside the core. So this graph is interesting, but we need to plot other graphs. I need to calculate the flux inside the core. So let's draw a line here, this line on x-axis, and I want to calculate By and plot By along this line. So let's analyze the problem again and plot B vectors along this line. You can see B. The B here is high, close to the inner radius. And for the outer radius is low. Yes, you know this. Because here we use this equation H. As long as we increase R, the length is higher, the H is lower, and the B is lower. But we calculated B at the center. So in the fields calculator, again, I want to plot By. Let's add it to the named expressions. I want to plot By along this polyline, By. So as you can see, for the inner radius, what is the distance? What is the distance? Distance, when we have one line in ANSYS Maxwell, and actually we are going to plot this graph. B along this edge. Distance is this one. Here, distance is 0. And if we move in this direction, for this point, distance is equal to the segment length. So this is distance. So here, you can see the variation of the B along the radius. For the inner radius, we have highest By. So what is the average value? The average value is 0.94. So here, what is the value of the B that we interpolated? B center 0.95, right? That is very close to this number. 0.949, that is 0.95 actually. So yes, we solved this problem using ANSYS Maxwell, and we know that the flux density is not constant along the radius. We have maximum flux density for minimum radius, minimum flux density for the maximum radius, but the average value, right, is okay for calculation of the flux inside the core. Here we calculated the average value of the flux density in the core, and we calculated the flux. So anyway, let's go for the next problem. Maybe for this problem 4, you can select other materials with different HP curves, export them and use them in MATLAB, recalculate it, use this equation and compare your solution with what you get in the ANSYS Maxwell software. So you can see when we know the concepts, when we know average values, when we can use average value, right, for what structures, simply we can calculate flux or inductance with these equations. So we can use a finite element software to validate our formulation, our equations. So, okay, so let's solve the next problem in the next video. Thanks for watching.